Okay, so in this video, we want to consider our first discussion of statistics. And the core idea of statistics is the following. How can you, from a sample of a population, infer something about the entire population? And a great example of this is the concept of confidence intervals. So our first example would be about confidence intervals for the mean of a population, the true mean of a population. Let's look at the following problem. We said that a factory manufactures products derived from apples. The company has very high standards and inspects the apples before transformation. A random sample of 80 apples was taken. So right away, let's write down what we know from the word problem. We have a sample of sorry about that, I had a technical problem. We have a sample of 80 apples, so let's say that n is our sample size. N equals 80. And what did we do with the sample? A sample mean weight. So we found the average weight of our sample. Now if you think of it, every apple will have most likely a different weight. So we could let xi be the weight of the ith apple selected. The weight is in kilograms. Okay, so here, since we are sampling at random 80 apples, that gives us 80 possibly different weights. Therefore, we have 80 random variables. We have x1, the weight of the first apple, x2, the weight of the second apple, up to x80, the weight of the 80th apple. And what are we saying? We weighted these apples and we found a sample mean weight of 0.146 kilograms. Well, the sample mean is simply the average weight of our sample of 80 apples. Well, how do we find the average of a sample? We add the values and divide by the size of our sample. As always, the average is denoted by a bar, so we'll have x bar is the sum of the weight of each apple divided by the total number of apples. And this will give us the average weight. And we have from our sample an average of 0.146 kilograms. Now here's where you have to be careful. This is now a random variable, and its value, we'll write smaller x, so lowercase x, x bar for the value. So what we have here is a random variable. We're saying if you are going to weigh 80 apples, here's how you would find the average weight. But here we have taken a sample of 80 apples, and we have obtained an average weight of 0.146 kilograms. And we also have obtained a sample standard deviation of 0.02 kilograms. This will be lowercase s, the sample standard deviation. So that's the information we have so far. With our sample of 80 apples, the average weight obtained was 0.146 kilograms, and the standard deviation of our sample was 0.02 kilograms. There's one other piece of information that we're told. Moreover, 8 apples were discarded as they were judged to be of inferior quality. So we have discarded 8 of the 80 apples. And this, you'll see, will be important in our third problem when we consider a confidence interval for a proportion. But right now, all we look at is a confidence interval for the true mean. And so we'll leave this piece of information out for the moment. So what is the question? The question is, part A, to construct a so-called 95% confidence interval for the true population mean weight, and that is for mu. Right? X bar is the mean weight we obtain from our sample of 80 apples. Mu is the true average weight of all the apples that the factory would ever process. And again, it's impossible to find mu exactly, because if you think of it, if the factory never goes under, well, they'll make their products for, in theory, forever. And so we have an infinite population of apples. So it's impossible to find the exact value of the mean. Now we want to find an estimate for the true value of the mean in what we call a confidence interval. Before we see how to build a confidence interval, all we need is a distribution for our random variable. We're talking here about the sample mean of our 80 apples, the sample mean weight. So we need to have a distribution for our random variable. Well, we can now use here the central limit theorem. We have an average of more than 30 random variables. So by the central limit theorem, the average weight will be approximately normal. We don't know the mean. This would be the true mean of the weight of the apples, and sigma would be the true deviation of the population of apples over, of course, root of n, where here n is 80. There's one little problem here. We don't know sigma. We only know an approximation to sigma being the sample deviation. And you'll see that we'll do two solutions for A. One where we cheat, we'll assume that sigma is 0.02, and the other one where we don't cheat and we take the sample standard deviation as it is. And this will allow us to introduce the so-called student's t distribution. Well, now we have to form here our statistic. If you think of it, you have a roughly normal random variable. Again, since n being 80 is way above 30. So now we know that we can standardize our sample mean. Right? If you take the random variable that is approximately normal, if you subtract from it the mean and you divide by its standard deviation, you have now standardized the random variable, and this is now approximately z, the standard normal random variable. And with this, we will be able to build our confidence interval. But as we've said before, we have a problem in that we don't know sigma. So let's do two solutions to part A. So we want a 95% confidence interval for the true population mean weight, thus for mu. So our first solution will be the one where we cheat. That will assume that sigma is 0.02. And then we'll see in solution 2 how we can fix the problem and no longer cheat. So recall what we have so far. We have our statistic that the average weight of a sample minus the true average over the true deviation over the root of n. This is roughly z, the standard normal random variable. From our sample of 80 apples, right, n is equal to 80, we sampled 80 apples. We found an average weight of 0.146 kilograms. And here's where we're going to cheat. We, from the sample, obtained a standard deviation of 0.02 kilograms. And if you look at our statistic, there's sigma here, but we don't know sigma. So here we'll cheat. We'll assume that 0.02 kilograms is not just the sample deviation, but actually the population standard deviation. And so we are cheating. And you'll see in our next solution where we stop cheating and we really use the sample deviation, therefore replacing sigma by s, this will slightly change our statistic. But for us, let's assume that we do have somehow found a way to obtain the true population standard deviation, and that is 0.02 kilograms. All right, we want to remember a so-called 95% confidence interval. So we'll let C. C is the so-called confidence level. And here we chose our confidence level to be 95%, therefore 0.95. And you'll see that from this point, there's really nothing new in the solution. So first, we have our statistic, which is the standard normal. Let us draw the standard normal distribution. This is our z-axis. The mean is 0, and the deviation is 1. So it looks roughly like this, with a mean of 0. And now the idea is, well, how do we use this confidence level? Well, the idea is we build a symmetric interval about 0, where the area inside the interval is 0.95. And we label the endpoints in the following fashion. We write little z c, because this value of z will depend on our confidence level. And we have a symmetric interval about 0, so the right endpoint is zc. Therefore, the negative endpoint, the left endpoint, sorry, is the negative. So negative zc. And now we complete our distribution. We want the area under this interval to be 0.95, the confidence level. We know the entire area of the normal distribution is 1. That leaves 5% for the two tail ends. By symmetry, they have the same area, so that leaves 2.5% for the right and the left tail. Therefore, 0.025, and the same for the left tail. And now we have the standard inverse z problem. We know if you look at the left endpoint, negative zc, we know the area to the left of negative zc is 0.025, and we want to find the corresponding z-score. So we use our table of the normal distribution, the first side, and we're looking for a probability closest to 0.025, so we can then extract the z-score. If you look in your table, the closest you can find to 0.025 actually is on the money, 0.025, and the z-score is negative 1.96. So the z-score is negative 1.96, and that is a value of this point right here. So we know from our table that negative zc is negative 1.96. Therefore, if you negate both sides, zc is just 1.96. And now let's see what we have. we will have a 95% confidence interval for z, and we will then solve for the mean. So look at this now. The area between negative 1.96 and 1.96 is 0.95. Therefore, the probability that the standard normal random variable lies between negative ZC and ZC, so negative 1.96, 1.96, is exactly 95%. And I will leave the ZC, the critical Z score, as ZC, and then in the end we'll replace it by the actual value. Because what we'll do now will work for any confidence level. So now think of it. We know that the probability that Z lying between these 2 points is 95%. So we now have an interval for Z, and we know that the probability that Z lies inside this interval is 95%. So we now have here a 95% confidence interval for the standard normal random variable, because we are 95% confident that the Z value will lie between negative ZC, ZC, therefore between negative 1.96 and 1.96. But we wanted a confidence interval for mu, the true population mean. But from the central limit theorem, we can replace Z by this value right here. So let's make the substitution. We are going to replace Z in our interval by x bar minus mu over sigma over root of n. So negative ZC, x bar, replacing Z minus mu, over sigma over root of n. And now, all we'll do is we will algebraically solve for the true population mean, and we're going to have an interval for the mean. This will be our 95% confidence interval. First, since we want to isolate mu, multiply both sides, so across the inequality, by sigma over root of n. So you'll get here negative ZC times sigma over root of n is at most. If you multiply this by sigma over root of n, it will cancel this on the bottom, and you'll be left with x bar minus mu, which will be at most ZC times sigma over root of n. We're trying to isolate for mu. Well, subtract x bar across, so you'll have here negative x bar minus ZC sigma over root of n is at most negative mu, and we subtract x bar from every term, so we'll get here negative x bar plus ZC sigma over root of n. And we're almost done. We wanted an interval for mu, not negative mu, so here we'll simply negate across the board. But here's where you have to be careful. What if I say that 2 is less than or equal to 3? This is true. What if I negate across the inequality? Let's see what happens. I negate 2, I negate 3. Now which is bigger? Negative 2 is bigger than negative 3. So you see, if you negate across an inequality, you have to reverse it. So we will here negate across, but these will become in the opposite direction. So if you negate this, we'll get x bar plus ZC sigma over root of n is greater than or equal to mu. Greater than or equal to, reverse the two inequalities. Negate this, you'll get x bar minus ZC sigma over the root of n. And we now have our 95% confidence interval for the true population mean, because we know the probability of this being true is the same as the probability of this being true, and we have chosen ZC to have a probability of exactly 95%. Let's rewrite this, because this looks rather strange because it's written backwards. So we are going to rewrite the inequalities, but we'll flip the order. At this point, you'll see that we are almost done. So we'll write this term first, which is x bar minus zc sigma over root of n is at most the true population mean weight of the apples, which is at most x bar plus the exact same quantity. And now, let's see where we go from here. We know this is true with 95% confidence. So we are 95% confident that the true population mean will lie between these two values. Now look at what we have here. We have x bar minus this value as the left-hand point of our interval. We have x bar plus this value as the right-hand point. And this is simply the error, which we call E. Visualize this on the real line. And you'll see what I mean by the error. You have x bar and you'll see that x bar is the center of the interval, because we add to x bar the sample mean, this value of E. So the right endpoint becomes x bar plus E, and the left endpoint is x bar minus the same amount, minus E. So we have an interval that is perfectly symmetric about the sample mean. And what we're saying right now is we are 95% confident that the true population mean will lie somewhere inside of this interval. So somewhere between x bar minus E, x bar plus E. We could be wrong. There is still a 5% probability that the mean will be outside of our interval. But we're 95% confident that the true mean will indeed lie inside of this interval. So we now have our 95% confidence interval. The only thing left is to calculate these quantities. Well, remember what we had. We've found a sample mean of 0.146 kilograms. We cheated and we assumed that we knew the true deviation to be 0.02 kilograms. We had a sample size of 80 apples, and our critical z-score we had found to be 1.96. Well, all we need is find the error. So let's find the error. The error is the critical z-score times sigma over the root of n. So let's plug in. The critical z-score is 1.96 times sigma, 0.02 kilograms, divided over the root of n, the root of 80. If you use your calculator to compute this, you'll have 1.96 times 0.02 divided by the square root of 80, and you will get approximately, we'll round up to the third decimal place, we'll get 0.00438 kilograms, and that's our error. And if you want your interval, you take the sample mean and you subtract the error, you'll get the left endpoint. The right endpoint, you take the sample mean and you add the error. So let's find our two left and the right endpoint. So x bar minus e is approximately, x bar plus e is approximately. So 0.146 minus the error, 0.00438, gives us approximately 0.14162. Now do the right endpoint, 0.146, plus the error, 0.00438, and we get approximately 0.15038. And now we have our 95% confidence interval for the true population mean. So let us write our conclusion. The left endpoint, 0.14162, is at most, if you just go back up, the mean, which is at most the right endpoint of our confidence interval. The right endpoint is roughly 0.15038. And this is our 95% confidence interval for the true population mean. And now think of why this is great. All we did was we took a sample of 80 apples. We found the sample mean weight, the sample standard deviation. We cheated here. We assumed that this was the true deviation, but we'll fix that in a minute. Then, just from a sample of 80 apples, we are able to conclude with 95% confidence that the interval from 0.14162 to 0.15039 will contain the true average weight of all apples. And this is what you would obtain if you weigh, in theory, all possible apples that will go through this factory. So we went from a measure of a sample of only 80 apples to a statement about the true mean weight of all possible apples being weighted. That's a really powerful statement. And if you look at why did I insist on doing it in full generality and not replacing the quantities by the variables in the beginning, is because no matter what problem you have for a confidence interval for a mean, this will always be the case. The left endpoint is x bar minus the error, the right endpoint x bar plus the error. The error will always be the critical z-score times the deviation over the root of n. So compute your error, add the error to the mean to get the right endpoint of your interval, subtract the error from the mean to get the left endpoint. So since we have done it in full generality, we can use now the result in every other example. Now, there's still something that should be or make you feel uneasy in the fact that we cheated. What we had obtained was the sample standard deviation of 0.02 kilograms, but we said, let's assume it's the true deviation. Let's see now we can fix this problem, right? And this will be what happens to this statistic if we replace sigma, which is assumed to be the true population standard deviation, by S, the actual deviation from the sample of 80 apples. And the only difference is we'll have a slightly different distribution, a slightly different score, but everything else of our solution will be exactly the same. And this will be our first introduction of a new distribution called the t distribution. So this is now our second solution where we are no longer cheating. And this is what you would do in real life. The other solution was just a warm-up example. So again, what did we have from our sample? We sampled 80 apples, so n equals 80. We found a sample mean weight of 0.146 kilograms. We found not the true deviation, but the sample standard deviation to be 0.02 kilograms. And we had our statistic, which was the following. If you remember, it was x bar minus the mean over sigma over root of n. And we are going to replace now sigma by the actual sample deviation and ask what will be our new distribution. So here's our statistic, the sample mean minus the true population mean over now s over root of n. And this will be, by the central limit theorem, not exactly normal. It will follow the so-called t distribution with degrees of freedom df. So df are the so-called degrees of freedom. And if you have a sample size of n, the degrees of freedom for this statistic happen to be n minus 1. Well, our sample is of size 80, and 80 minus 1 is simply 79. And now we're good to go. The only difference from before is we'll have a different distribution, which will give us different critical values. Everything else will be the same. And you may ask, well, what does this distribution look like? The answer is it looks exactly like the standard normal distribution, except that it has heavier tails and is lower around 0. But it is still perfectly symmetric about the mean, which is equal to 0. So we draw our t distribution. These will be values of t, not z. And draw the curve with heavier tails but slightly lower central part. The mean is still 0. And as before, we want a 95% confidence interval. So we want to have a positive t-score, tc, because this will depend on the confidence level. We want, again, it to be symmetric about the mean. So we'll go from negative tc to positive tc. And again, we want a 95% confidence interval. So the area between negative tc and tc is 0.95. This leaves 5% for the two tail ends. By symmetry, this leaves 2.5% for the right and the left tail. And the question is now, well, how do we find the critical t-score? Right, our confidence level, remember, was 95%. So we use the table for the t distribution. And you'll see that it's quite easy to read. It will depend on the degrees of freedom and the area to the right, as you will see from the picture. So here's the t distribution. You see it looks a lot like the standard normal distribution. The mean is 0. And now the table entries are the t-scores. So these values are the t-scores. And to find the t-score, you need two things. df, the degrees of freedom on the left, most column, and alpha is the area to the right of the corresponding t-score, which are given in the top row. Well, let's look at our picture. So to find the value of t, we need alpha, the area to the right of the t-score, and the degrees of freedom. So let's see here. Here's our t-score. The area to the right is 0.025. The degrees of freedom are 79. So we look for 0.025. There it is. That's the area to the right. And the degrees of freedom, let's go down, and you see there are gaps. And here we jump from 40 to 45, and we end up here with 60 and 90. Well, 79 is in between, and we just picked the closest one to 79, and that is 90. 90 is closer to 79 than 60, so we'll take 90, and if you go back up, alpha was 0.025, so we go down, and if we use 90, the t-score is roughly 1.987. So we have from the table our t-score, roughly 1.987. And now we're good to go. But we won't rederive the interval again. It's the same as before. Instead of now the z-score that we had in the previous example, it will be replaced by the t-score. So I'll remind you of what we had obtained as our 95% confidence interval from the previous solution. It was the sample mean minus the critical z-score times sigma over root of n. This was less than the true mean weight, which was less than the sample mean, plus the critical z-score, sigma over root of n. The solution in our case will be the same. Instead of the critical z-score, we have the critical t-score, and instead of the true deviation, sigma, we have the sample standard deviation, and this will be the differences. So x bar minus tc s over root of n is at most mu is at most x bar plus tc s over root of n. And as before, this is now your error. Let's compute the error. The critical t-score times s over the root of n. The critical t-score is 1.987 approximately times s, which was 0.02 over the root of 80. This will be approximately 1.987 times 0.02 divided by the root of 80, 0.00444. And if you notice something interesting here is the error in this case is a little bigger than the error in the previous solution. In the previous solution it was 0.0438. And why does it make sense that we have a larger error? If you think about it, since we did not cheat, we assume that we had only the sample deviation, but the true population deviation. That means we have less information. The less information you have, the more uncertainty there is, therefore the bigger the error of your approximation. And that is why we have a slightly larger error in this case. So finally, we find the left-hand point of our interval, x bar minus the error, the right-hand point, x bar plus the error. X bar, remember, was 0.146 minus 0.00444 gives you approximately 0.14156. Now the sample mean plus the error, 0.15044. And now we have our conclusion. Our left-hand point the mean, the right-hand point of our interval, is our 95% confidence interval for the true mean weight of an apple, the true average weight of all the apples going through the factory. So what we can say now is and imagine how powerful this statement is. We took a sample of 80 apples only, and here in our second solution, we did not cheat. Everything we used was from the sample that we have collected. We sampled 80 apples. We found an average weight of 0.146 kilograms, a deviation of 0.02 kilograms, and from only sampling 80 apples, we are able to say that we are 95% confident that the true average weight of all apples will lie between roughly 156 kilograms to 0.15044 kilograms. And that is a statement again about the entire average of all apples. Of course, we could be wrong because we're only confident in this up to 95%. So there's still a 5% chance that the mean is not contained inside of our interval. But 95% is pretty darn good. And this is really the power of statistics, extracting from a small sample of the population a statement about a parameter, a measure of the entire population. So in real life, you will not get the true deviation, but the sample deviation. And the only difference, instead of the z distribution, you get the t distribution. You find the critical t-score. Everything else works the same. Instead of a z-score, you have a t-score. Instead of sigma, you get s. Now, let's answer problem B. And this will, as you'll see, will be very, very short. Let's go back to the question. In B, we're asking a different question. We're asking how large should your sample be? So now we're saying how big of a sample should you take? So we're asking to find n, the sample size. If you want to be 95% confident, that is our confidence level, that the sample mean weight is within 0.003 kilograms of the true population mean. If you think of it, this is your error. We want the sample mean weight with 90% confidence to be within, no further away from the true population mean than 0.003 kilograms. So let's just write down what we know and what we want, and you'll see that with what we have so far, this is quite easy. We were asking how large of a sample should we take. So again, this is B. So we want to find n. N is the size of your sample. And we're asking how big should we choose n? How big of a sample should we take if we want to be 90% confident? That's what we know. So the confidence level is 90%, therefore 0.9. That the sample mean is within 0.003 kilograms of the true population mean. That is your error, right? The distance between the sample mean and the true population mean is the error between the exact and the approximate value. So the error is 0.003. Well, if you go back to what we have derived previously, we know the error is simply the critical z-score times the deviation over the root of n. There's only one thing here. In reality, what we have is not the z-score but the t-score, right? So really what we have is not this, but it is the t-score times s over the root of n. The only problem with this, if you remember, to find the t-score you need two things. The area to the right of the t-score, but also the degrees of freedom. The degrees of freedom are equal to n minus 1, but we don't know what n is, so we don't know the degrees of freedom. So it seems that we're stuck. But if you look at the two tables, you'll find that when n is large, the t-score is really close to the z-score. And the reason for this is the following. In real life, you'll want to have a small error. And to have a small error, you will need a big sample. So n will have to be large. And what is true about the t and the z distribution is the following. The t distribution gets closer and closer to the z distribution as the degrees of freedom, therefore n minus 1, become bigger. And because again, in real life, you will want a small error, this will imply a slightly or a large sample, therefore the t distribution will be really close to the z distribution. So we can here make an exception because all you really want in real life when you ask for a sample size is a ballpark figure. Should your sample be in the hundreds, in the thousands, and so forth, so it's okay here to approximate the t-score with a critical z-score. And now if you look at this, well, we know E. So we know E here. Let me write this here. So we know E. We know S. S, remember, was 0.02 kilograms. So we know S, we know E. We want to solve for N, and because we know the confidence level, we can find the corresponding z-score. So we will know everything here other than the root of n, and therefore we can finally solve for n. Let us find our critical z-score. As always, we draw the distribution. Here we have the z distribution, symmetric about 0. We want a 90% confidence level, so we break up the interval into 3 parts. ZC the right-hand point, negative ZC the left-hand point. The area in the middle is the confidence level, so 0.9. That leaves 10% of the two tail ends. By symmetry, they have the same area, therefore 5% for each. And now we can use our table for the normal distribution. Let's find negative ZC because the area below negative ZC, the negative of the z-score, is 5%. So we're going to hunt down in our probability table the closest value to 0.05. So let's see. If you look right here, the probability is 0.0495. Here it's 0.0505. They're both equally close to 5%. You can pick, when you have a tie like this, either one. Let's pick, say, this one. So then with a probability to the left of roughly 5%, the z-score is negative 1.6. If we go up, negative 1.65. And that was the value of negative ZC. Therefore, if negative ZC is negative 1.65, the critical z-score is positive 1.65. And now we're good to go. If you go back to the equality here, or at least the rough equality, we know E, we know ZC now, 1.65, we know S, so we can solve for N. Let me rewrite this as an equality. So the error is the critical z-score times the deviation over the root of n. To solve for root of n first, multiply root of n up top, divide by e, and you'll have that root of n is the critical score times the deviation over the error. If you want to solve for n, square both sides. So squaring the root of n gives you back n equals the square of the z-score times s over the error. And now we can replace. The z-score we found to be 1.65 times the standard deviation of our sample that we found to be 0.02 over the error, and we wanted an error, remember, of 0.003, and this was in kilograms. So 0.003, and we're squaring this. So let's compute now. So 1.65 times 0.02 divided by 0.003, you get 11. Quite surprisingly, exactly 11. And if you square 11, you get 121. And that's your answer. So you see, if, in the end, your sample is of roughly size 111, so if you take a sample of approximately 121 apples, and you weigh them, you will be 90% confident that the error between the average weight you will obtain from your sample of 121 apples and the true average weight of an apple will be no more than about 0.003 kilograms. And that is how you find from a confidence level and a prescribed error and a deviation the size of your sample. This concludes our first example of confidence intervals for the true population mean mu.